Hello everyone. We now continue the example from last study. We consider four streams of two hot and two cold stream. According to this system, what we got under the circumference of delta T minimum equal to 10 degrees Celsius, we found that hot pinch will be equal to 90, cold pinch will be equal to 80 degrees Celsius. In addition of that, the minimum requirement for hot utility is 50 and the minimum requirement of cold utility is 30 kilowatt. So next, what we need to do is to find out for the network. So according to this, of course, we would have two regions, one as above and one is below. So let me consider for the above pinch first, above pinch region. Now, the first step is to draw the line based on these two pinch value. So what we have is 180 degrees Celsius go to 90 here. This is at the pinch point. And 150 go to 90 degrees Celsius. This is hot pinch, hot stream and hot stream. The one with cold stream, I put in red here. So we have from 135 degrees Celsius down to cold pinch, which is 80, and 140 down to 80 degrees Celsius. This will be cold number 1 and cold number 2. This is hot number 1 and hot number 2. So the criteria that we use to make the network here is that Cp hot less than or equal to Cp cold. Cp all capital here is refer to the heat capacity flow rate. So this will be, the unit of this will be kilowatt per degree Celsius, as we mentioned before. So the next step is to find out how much of the heat load for each stream here, so we can consider whether they can exchange the heat or not. So the heat load on each stream is that Q equal to Cp multiplied with delta T for each stream. So what we have here, the heat load for the first stream is equal to 3 is a Cp, multiplied with the difference of temperature here is 90, so become 270. The Cp for H2 is 1. So what we get here, 1 multiplied with 60, it is 60 here. The unit is kilowatt, of course. How about C1? C1 has Cp equal to 2. So 2 multiplied with 55 become 110. And then the last one, C2, has Cp equal to 4.5. This will multiply with 60 here. So what we get is 270. Okay. Now let's see what is which connection can be possible. So the possible link would be Cp hot less than or equal to Cp cold. So can we consider that? So the possible would be from that to this. So I write down H1 to C2 and the other one is H2 to C1 because Cp hot less than Cp cold. H2 and C1. Now let's see what can we do first. Of course, by H1 and C2, H1 contains the heat load at the same amount of C2, which is in the possible link. So that would be very easy. So this link will consume all the heat load of 270. So you don't need to consider for the the temperature, the exit temperature of this heat exchanger because they consume all the heat that required for these two streams. How about this side? The less is H2 and C1. So if I put the link here, H2 and C1, H2 contains only 60 kilowatt. C1 contains 110. So to consume, to make the heat exchange, the maximum that they can do is 60 kilowatt here. And the less would be another 50 because no more link between cold to hot stream. There is no more hot heat load that can provide to the cold side. So in this case, start from the pinch line to the left. So it looks like we would like to increase the temperature from 80 degrees Celsius to higher one. So this one utility that we need to add into the system must be QH. And this QH, the hot utility look like is similar to the one that we got from the cascade or graphical method based on the minimum values. So it looks nice. You can go to page number 132, which is another requirement that do not use hot utility below the pinch. This is above pinch. And do not use the cold utility above the pinch. We don't have the cold utility here, but we do have only hot utility. So we meet all the requirements or the criteria. So now, the conclusion on above pinch is that we need 2 heat exchangers and 1 heater, 1 utility of heater. Now let's go to the one below pinch. Do the same thing. So we draw the line and find out for the heat load on each stream. So according to this, we draw the line until we meet the temperature at 60 degrees Celsius. This one go to 30. This one, the cold one go to 20. And we don't need to draw that because it's already meet the point of the supply temperature of 80 degrees Celsius on stream number C2. So the next step is to find out for the heat load for the below pinch, below the pinch point. Heat load of that equal to, this is just write down to refer. So the heat load of this stream is 3 Cp multiplied with the temperature gap. So become 90. 1 multiplied with the temperature gap, 60. and 60 multiplied with 2, it is 120. Okay. I have to go back a little bit on the above pinch to check that all the temperature excess from the heat exchanger will not against the second law of thermodynamics. So it starts from the first heat exchanger here. We have the outlet of the hot stream equal to 90 and the inlet of the cold stream equal to 80. So the gap is about 10. So it is okay. How about this side? Our inlet and outlet, the gap is higher than that one. So look like it doesn't against the second law of thermodynamics. So this heat exchanger is possible. So how about the second one? The second one here, this one is okay. So what we need is to find out the temperature outlet of this as well. So to determine the temperature outlet here, it's become from the very simple equation is that Q equal to, Q is the load, equal to Cp on that stream and delta T. So what we have is 60 equal to the Cp equal to here, and the temperature between this point and that point is T minus 80. So what I get is temperature will be equal to 110. Right there is 110. So the temperature inlet and outlet, inlet in hot stream and outlet of cold stream, the gap of this temperature higher than the minimum temperature gap. So this heat exchanger is possible as well. So look like the above pinch is fine. So come to this point, come back to the below pinch. The criteria on this one will be different from that, but in case that we don't know what to do first, we just fix to the criteria. So Cp hot must be greater or equal to Cp cold. So let's see which the connection would be possible. So this has 3, 1, 2 in terms of Cp. So it looks like we want that. We can have that, right? So let's do that. How much that can be exchanged? The whole thing. Check the temperature that against the second law or not. No, this is not the total. The heat that can be transferred, something left. So you need to find out the temperature inlet here. So what is it? This is come from the equation of 90 equal to 2 Cp and 80 minus T. This represents the cold stream inlet. So the T, small t here will be equal to 35. So can you check that? Yes, this 35 and 60, they do not, and this gap value doesn't against the second law, so this heat exchanger is acceptable. Now, this stream, the remaining of the heat load on this stream will be 120 minus 30, and that minus 30 becomes 30 here. The stream here still have 30 left, 30 kilowatt left. So next step, we don't need to consider on that, just make the connection of this and check for the temperature in and out. So that and hot stream requires 60 kilowatt of heat load. If I use that for the whole thing, so it means I need to find out for that temperature. Because we need to consider from the pinch line to the right hand side. So the temperature here will be from 30 equal to Cp on this steam line 1 by 90 minus T. So this T will be 60. Does it look okay? This is 30, 35, 35 and 90. Okay. 60 and 20. Okay. So the remaining heat load, because it's consumed 30 already, the total they require is 60 kilowatt. So the remaining become 30 here. And the heat requirement here as the utility used to reduce the temperature from 60 to 30 degrees Celsius. So what kind of utility that we want? Must be QC, because you would like to reduce the temperature to 30 degrees Celsius from the higher one. So QC is put here, which is equal to what we get from the number that we calculate from the graphical method. So in this side, we found that 2 heat exchangers is required plus 1 cooling system. Totally what we have here, if I put it together, so it takes 4 heat exchanger plus 2 utility. 2 heat exchanger plus 2 utility. So is that acceptable or not? Just go to page 137 in this handout, and then they said that the minimum heat exchanger including the utility will be less on that, on this equation, Z min equal to N dash plus L dash minus S. And this is the minimum equipment that put in here. What we have is the equipment that put in here is 6, right? So now we will use this equation to find out the number is okay or acceptable or not. N dash is the number of streams including the utility. So what I have is including the utility. So what I have is 4 plus 2. Of course, this utility, this is the 4 stream. Plus L dash. L dash is the internal loops. Loop. If you go back to this diagram, do you have the loop here? Yes. Look at this. The connection between H2 and C1, There are two heat exchangers that connect between these 2 streams. And of course, this is what we call loop. So what I have is one loop present in the system, and then minus S. S is the number of independent branch subset that exist in the network. So we don't have that. So this is become 6 plus 1 becomes 7. What we have is 6. Ooh. Is that right? Something wrong, huh? Or I don't think this is the one that include the utility. So let's see. What the minimum heat exchanger must be 5. So in this case, we have 6. So what we have to do is to, next step is to loop baking. We have to do the loop baking. Okay? All right? So that's all for this example. Now, according to the stream law that we can extract from the process flow diagram, we calculate for the pinch points, we calculate for the minimum requirement for utility from both sides, and then we can understand the connection, the network of heat exchanger in the system. And we can make a judgment that how the heat exchanger, the number of heat exchanger that we receive from our consideration is too much or too less compared to the minimum equipment that they suggest from the theory. Okay, that's all for this example. Thank you, and see you next example.